So we've already had an introduction looking at integrated rate law expressions. And now what we want to do is look at some examples of this. We're going to go ahead and work through some examples of looking at integrated rate law expressions and how they relate to general rate law expressions. Now this table here gives us kind of an overview of how our general rate law relates to the integrated rate law, and then how that relates to like our half-life expression, and reminding us our half-life is the time it takes to get to half of whatever our original concentration was, and like depending on the type of the order of the reaction, we'll see that depends on our rate constant, maybe our initial concentration. We'll notice for like first order, there's no dependence on the original concentration for how long our half-life is. But what we see is that because the order of the reactant affects how much our rate changes as that concentration decreases, that's going to affect how our concentration is calculated over a certain amount of time. So we have these three different orders. 0, 1, and 2 are typical reaction orders that we'll see. They have specific rate law expressions that we can utilize. And we notice that if we know what the order is, or if we know what our rate law expression is, we can identify what our order is, right? If it's 0 order, we won't even see it here, right? It'll be, our rate is just equal to our rate constant, it's constant. If it's first order, we'll only see that concentration of that reactant to the first order. If it's second order, second order. Each of those have a corresponding integrated rate law expression that is able to relate concentration over time. Just to remind us, our general rate law is looking at the rate and how that relates to concentration, whereas our integrated rate law is looking at how our concentration is related to how long how much it changes over a time period. And then we also see our rate constant tells us something about what our order is, because that rate constant is specific for a first order, 0 order, or second order. For example, every second order rate constant is going to have, for our overall reaction, an inverse concentration unit times an inverse time unit. So that could be molarity per second, or inverse molarity, inverse seconds. It could be inverse millimolarity, inverse minutes. It just depends on how fast or how slow that reaction is happening. Now with this as a background, we're going to go ahead and work through an example problem here. Our example is that the hydrolysis of sucrose into glucose and fructose, so we have our reaction here, has a rate constant of 1.8 times 10 to the negative fourth inverse seconds. So let's go ahead and write that over here. 1.8 times 10 to the negative fourth inverse seconds at 35 degrees Celsius. Again, reminding us that that rate constant is temperature dependent. Their experimentation, the reaction rate was found to be 0 order with respect to H2O. So if I were to write my general rate law expression, it would be rate equals K times our water concentration to some power. And then I'm going to just go ahead and write sucrose instead of C12H22O11, just to shorten as we're writing this, times our sucrose concentration to some power. And through various experimentation, it was found to be 0 order. So that means that M is 0 with respect to water, and then first order with respect to sucrose. So that tells us that N is 1. So now we can simplify this and say our rate is K, sucrose concentration to the first order. And also, if we're looking at 35 degrees Celsius, we could also maybe even narrow it down even more and say our reaction rate is equal to our rate constant, 1.8 times 10 to the negative fourth inverse seconds times the concentration of sucrose to the first order. And so we got that all from the information we knew about our rate constant, and then maybe we had collected some data already before about the order with respect to sucrose and water. So now we have our overall reaction, and we're going to look at a few questions related to that. The first one is that we're told that the solution contained 0.25 molarity sucrose initially at 35 degrees Celsius. We want to calculate the concentration of sucrose after 195 minutes of reaction. And again, we're looking at concentration and time. So anytime we're trying to relate concentration and time, that lets us know we want to use an integrated rate law expression. And thinking about which one we may want to use. Again, we're going to scroll up here to our table. We have 0, first, and second order. We know that this reaction here is first order. So that means I could use either this expression or this expression. So I'm going to go ahead and write both of those down there. So we have the concentration of sucrose at some time equals our original concentration of sucrose times e to the negative kt. And then we also have the natural log of the concentration of sucrose equals the natural log at some time of sucrose initially minus k times t. So we notice there's two expressions here. They're all relating four variables: concentration of sucrose initially at some time, and then our k value and time t. Now, which of these maybe would we want to use? The reason why we're provided these two is that one is more simple in calculating for either K, T, or sucrose concentrations. So if we're looking at this and we see our K and T are inside of a function, what that lets us know is that this is better if we're trying to solve for one of our concentrations, either our original concentration or concentration after some time, because those are outside of our function here. Whereas we notice here we have sucrose at some time, our initial sucrose concentration, K and T. That lets us know this is easier when we're solving for either a K value that we don't know or the time that it took for a reaction to occur. And so here we'll see, because our sucrose concentrations are inside of our function, it's easier just to plug those in and solve for something outside of an e or a natural log function. We can go back and forth between each of these. It's just one is easier than the other in solving this. So we look here and we see we're trying to find the concentration after a certain amount of time. And so because of that, what we see here is that maybe we probably want to use this one here, just because it's a little bit easier in solving for our concentration. So let's do that. The sucrose concentration at, I'm just going to put 195 minutes, is equal to our original sucrose concentration, 0.250 molarity, times e to the negative, and our k value, 1.80, times 10 to the negative fourth inverse seconds. And what we notice here is that our time that we have for our k value is in seconds, whereas our time that we're given here is in minutes. And so we want to make sure those are the same units, because whatever we're raising e to some power needs to be unitless. And so if we see here, we convert 195 minutes to seconds, right? We would multiply by 60 and we would get 11,700 seconds. So we can go ahead and plug that in here. And so now we have the amount of time that our reaction has occurred, and let's go ahead and make sure that we're going to get the right units there that cancel out. And so what we'll find once we go ahead and calculate this is that the sucrose concentration after 195 minutes is going to be 0.0304 molarity. So that's the amount of time, the concentration that we would have after 195 minutes. And again, reminding us that we're trying to concentration versus time, and we knew that this was first order, so that's why we looked at those two integrated rate law expressions. Now next, we want to calculate question 2, the reaction rate after 195 minutes of reaction. Well, now we're looking at rate, and we're now looking at, well, after or at that amount of time, which is going to correspond to a specific concentration. Because now our concentration after 195 minutes is our 0.0304 molarity. So anytime we're trying to determine the reaction rate, that should always bring us to our general rate law expression, or in this case, because we know what our k value is, 1.80 times 10 to the negative fourth inverse seconds. And then we now want to look at the concentration of sucrose raised to the first order. Now, it's not our original concentration. Our original concentration was 0.250. Now it's decreased after 195 minutes to 0.0304. So if we want to look at the rate, after 195 minutes, we're going to use the concentration of sucrose is now 0.0304 molarity. It's no longer the 0.250 molarity. So we can go ahead and plug that in here now for our rate. Our rate constant, 1.8 times 10 to the negative fourth inverse seconds. Our concentration here again, 0.0304 molarity. And so we would find that our rate at 195 minutes is 5.48 times 10 to the negative sixth molarity per second, right? Because we have inverse seconds and then concentration molarity per second. And that would be our rate there. If we were looking at original reaction rate, we'd look at the sucrose concentration we originally started with. Again, reminding us anytime we're focusing on our reaction rate, we want to go back to our rate law expression. And we notice we just need to know our K value and the concentration of the reactants or reactant that is affecting our reaction rate. So now we have the reaction rate after 195 minutes. We would notice this is slower than our original reaction rate, and that's because our concentration is lower. Next, let's now switch the variables that we're going to identify. We want to figure out how long in minutes will it take for the sucrose concentration to decrease down to 0.1 molarity. Again, we're dealing with a first order reaction, and here we're thinking about time and known concentration. And again, we're trying to relate those two variables. That means we want to look at what our integrated rate law expressions are. And again, we have one of two that we can choose from. We can use the one that we used before, where we could say our sucrose concentration at some time is equal to our original sucrose concentration, e to the negative kt. And again, at this time, we're solving for our time instead of for our concentrations. So maybe it might be a little bit easier just mathematically to look at our other expression, where we could have the natural log of our sucrose concentration at some time equals the natural log of our original sucrose concentration minus k times t, because now we're going to solve for this time, which is outside of a function, and just makes it a little bit simpler mathematically. And so now we know our sucrose concentrations, we know what our K value is, and we're going to solve for T. So let's plug in the information that we know. We have 0.1 molarity is our original concentration, our concentration after some amount of time. We're figuring out how long it takes to get there. Our original concentration was 0.25 molarity. Our K value is going to be 1.80 times 10 to the negative fourth inverse seconds times time. We do a little bit of algebra, and we find that our time is equal to 5,090. And if we think about what units are there, we see here that we have inverse seconds, so that means that our time is going to be in the same units, and that's in seconds. However, we notice we're trying to identify our time in minutes, so let's go ahead and convert that to minutes, and we would find that this is going to take 84.8 minutes for the concentration to decrease from 0.25 down to 0.1 molarity. And again, we're thinking about there's basically four variables that we're looking at here: concentration, time, our K value, and then our rate law expression, which is our reaction rate. And we have the ability to relate those with either our integrated rate law. So we think about our rate law is looking at how our rate relates to concentration. We're thinking about those variables, whereas our integrated rate law is thinking about how our concentration is changing over some time period. And we have the ability to relate those variables. We notice here kind of the linker is our concentration, and a concentration at a specific amount of time perhaps. And we notice also for both of these, we're dealing with the same K value, unless we've changed our temperature, but we're dealing with the same K value for our reaction because we got our integrated rate laws by doing a little bit of calculus from our original rate law expression to integrate them and get to our integrated rate law expression. So now what I'm going to do is I'm going to give you a practice problem. And why don't you go ahead and pause your video and answer this question. For a specific drug to maintain To remain out for sale on a shelf, the concentration of the active ingredient must have decreased by less than 5% of the original concentration. The shelf life is defined as the amount of time it takes for the active ingredient concentration to decrease by 5% of the original concentration. So decrease by, think about what that means. The starting concentration of an active ingredient was 5.20 millimolarity in the bottle of an over-the-counter drug. The reaction is zero order, so that tells us something, for the decomposition of the active ingredient, and the rate constant is 3.6 times 10 to the negative 6 millimolarity per day. So we want to figure out the shelf life in years. So why don't you go ahead and pause the video and solve for that shelf lifetime. So now as you've had a chance maybe to work on this, as you pause your video, let's go ahead and work through this really quickly. So we know that it's zero order, and what that means is we're going to use the integrated rate law expression, where we have A at some time equals our original concentration minus KT. We think, which of these do we know? We know the concentration at some time, the original concentration, and we know our K value. So we're trying to figure out how long it takes to decrease by 5%. So if we're told that we decrease by 5%, what that would tell us is that we have 95% remaining. Right? We think 100 minus 5% that is decreased by. Okay. Important to note there, these are some things to pay attention to. Decrease by is how much it dropped by. Decrease to is what the ending concentration would be. So it decreased by 5%. And so now we have our fraction of how much is remaining, and we knew how much we originally started with. So we could say the concentration at some time is going to be our original concentration, 5.2 millimolarity, and then we're going to have 95% of that, or we can multiply it by 0.95, and we would have 4.94 millimolarity remaining. So now we can go ahead and plug that into our integrated rate law expression here, where we know those variables. So we have 4.94 millimolarity equals our original concentration minus our K value, 3.6 times 10 to the negative fourth millimolarity per day. And then we're going to go ahead and solve for time. And once we go ahead and solve for time, we'll see again reminding us that whatever units our rate constant is using for time, that's what we're going to have for our time value when we solve for it. And so that would be 722 days. And in this case, we're looking for years. And so we can go ahead and convert that to years, and that would be 1.98 years. So this drug could be on the shelf for about 2 years before it has to be removed.